Hello students, welcome to the physics section. We will have a brief discussion about rolling motion from the chapter System of Particles and Rotational Motion at 9:10 p.m. Okay, so try to attend the session by 9:10 p.m. guys. Okay, it is all. Let us meet at 9:10. Till then, take care. Bye bye. Yes, everyone. Yes, welcome back to the physics session. We have duster. Someone can go and get a duster. Now discuss about. Law of conservation of angular momentum. So the last concept left over is rolling motion, or we call it as pure rolling. Pure rolling. It's not working. Right. So write down next subheading rolling motion. Rolling motion, they also call this as pure rolling. Pure rolling. What does this mean? We have discussed in this chapter till now different concepts like center of mass of discrete particle system, of continuous mass bodies and removed mass bodies, and moment of inertia, its calculations in different cases, discrete particles and continuous mass bodies by using parallel axis theorem, perpendicular axis theorem, etc. And rotational dynamics like angular variables, angular displacement, angular velocity, angular momentum, and torque, and law of conservation of angular momentum also. While dealing with those, while discussing those parameters, we have discussed about usually we have discussed about rotational motion. But here rolling motion means, to understand this, let us consider a disc or a spherical body on a surface. Its center or center of mass is here at its geometric center. Rolling is nothing but it is a summation of or combination of both translation and rotation, or translational motion and rotational motion together will be called as rolling motion or pure rolling. Okay. So whenever a body is, say for example, rolling, that means center of mass will be in what? Translatory motion. Translatory motion. So you can say this is velocity of center of mass. Velocity of center of mass. Whereas every other particle, say a particle here will undergo what kind of motion? Circular motion. A particle here will undergo circular motion. A particle here will undergo circular motion. Is it clear? So this can be called as a rotation. Rotation, rolling, circular motion about a particular point called, this is reference point. So rotation. So this combination of what you call translation motion plus rotation motion is called rolling motion. Or simply you can write it here. Rolling is equal to translation plus rotation. Rotation will be about the fixed axis. Translation is what? Linear, rectilinear motion. Some of these two will give you rolling motion or rolling. Is it clear? Right. Whenever a body is in rolling motion, here in this case we deal with few simple points. We consider some points like here a point A, here a point B, and some intermediate point. Let us say this is A, B, C, D like this. Whenever only consider a point or a particle on the circumference, so as it will be about this point, it will be rotating and moving forward. So this point will be in spiral motion. It will be under helical motion or spiral motion. We are not getting into the details of those complex motion called spiral motion, but only this will concentrate on rolling, which is a translation plus rotation. If you observe here once again, the particle at this point, at a given point, the velocity of the particle is given by a tangent drawn at this point in the direction of rotation or rolling. Whereas for this particle, as it is rolling in this direction, the tangent drawn in this direction gives velocity at that point of the particle at that particular point. Whereas for this particle, tangent will give you velocity of this particle or particle here at a given instant of time. Or similarly for this particle also, the tangent gives the direction of velocity. Direction of velocity for these particles will be different in different directions. Whereas for the particle or for a point which is here called center of mass will always be in translation. Now if you observe the total velocity of the rolling body or the total velocity of any point you observe, every point will be moving forward and will be in rotational motion also. So because this point also moving forward, after some time it will be here, as the entire this will be here. So with what velocity it is moving forward? It is moving forward the same velocity as that of the center of mass. The center of mass. Do you follow this? So this also will move forward with the velocity of center of mass, VCM, and also with the tangential velocity. Tangential velocity. This tangential velocity can be represented in terms of rotational variables. Can be represented in terms of rotational variables. We know what is the relation between the linear and angular variables, right? V is equal to R omega. So when a disc or sphere is rolling, we will be rotating about this axis with a velocity called angular velocity omega. And this is given by this, about this axis. So this Vt, tangential velocity is nothing but its radius is R omega. R omega. Now, am I here? At point A, B, C or other points, what is total velocity? At A, total velocity is, if it is moving forward, Z is nothing but, what do you call it? This rotational component is this, tangential velocity, but it is VCM. So the total velocity at A is, VA is equal to VCM. It is, the tangential velocity is exactly in opposite direction. So you can take it as minus Vt in vector form. Is it clear? That gives you the total velocity of the particle at point A in rolling motion. So magnitude of this, if you want, because it is in what you call vector form, VA can be expressed as square root of VCM square plus what? VT square. Right? So plus both are what do you call x direction only, right? X axis only. But it is in positive x axis, this is negative x axis. So if you square, you get the same. But here you can take tangential velocity is equal to r omega. So in terms of this, it can also be expressed as square root of VCM square plus r omega r square omega square also. So based on rolling motion, this kind of questions you will get. Say for example, if you are given a disc, if you have given a disc of radius r and velocity to find, if radius of the disc is given and your velocity is given, the velocity to find what is the velocity of the point which is in contact with the surface if VCM if it is moving forward, usually what you call total velocity of this point will be vector sum of this. So if both are equal in magnitude, this and this, then resultant velocity will be 0. In such case, this point appears to be at rest always. Only this point, it appears to be at rest always. That we can take it here. If VCM is equal to VT, that is r omega, then point A is considered to be at rest always. Is at rest always, and this is considered as a condition for pure rolling. If any one of this is greater, then the body will not be in pure rolling. So if, for example, this is greater than this, so this means the body will be dragged forward. This is greater than this will be dragged, means it will slip. So for example, when a vehicle is made, if some mud comes on the way because of rain, so even though the vehicle tries to move forward, but the tires will skid. Skid means this velocity will be more than the forward velocity. So the velocity, the body will not move forward. Is it clear? Whereas in some cases, if you take if the body, if the wheel is moving on a surface, or let's say an inclined surface or a horizontal surface, but it is, instead of rotating, the entire wheel is skidding downward or skidding forward. That means this will be greater than this. So it will skid forward or slide forward. It will slide forward, the forward velocity is greater than this. The backward velocity is greater than this, you can call it as undergoing backward sliding motion or skidding motion. If it is greater, it will undergo forward skidding or sliding motion. Both are equal, it undergoes pure rolling motion. So this is, that's why it is called as, this one is called r omega. VT is condition for pure rolling. It is another pure rolling. The point, what is this? Then the point A is, the point A is at rest always. This is the condition for pure rolling. So write down this as a note. We get a question, direct question like this. Condition for pure rolling. Condition for pure rolling is VCM is equal to VT is equal to r omega. VCM is equal to VT is equal to r omega. Okay? Whereas, what about under pure rolling, velocity at point A is 0. What about the other velocities of other points? Let us see. So write down, let's see, next some reading. For pure rolling, only for pure rolling we will discuss how. Now we have a diagram. So for pure rolling, if you consider this is the body on the surface, this is point A, this is B. So this is one diameter, this is another diameter. So this is center of mass. So center of mass is moving to velocity of VCM. So this will be at rest. Velocity of under pure rolling, you can see the first point. Velocity of A will be equal to 0. Next, second point. Velocity of B. Velocity of B. What is velocity of B? So due to this forward motion, VCM will be in this direction, or due to tangential velocity, this will be in this direction. This is equal to r omega. So velocity of B is nothing but sum of these two. What is that? VCM plus VT or VCM plus R omega is nothing but velocity at B. Velocity A equal to 0 in pure rolling. In pure rolling, we take this. In pure rolling. Pure rolling. So what about velocity at this point? This is C and this is D. So here this point also move with the same velocity of VCM forward, but tangential velocity is in this direction. Vt is equal to R omega. So the net velocity is in this direction. This total velocity are Vc. So Vc is equal to third point. Vc is equal to what? These two are making an angle of 90 degrees with respect to one another. So this is in positive direction, this is negative direction. VCM I cap minus Vt j cap. So vector form if you write vector form VCM I cap minus Vt j cap. That is nothing but R omega j cap. So magnitude of this is given by Vc is equal to. Is this visible?
Yes.
Not visible. So we can say Vc is equal to magnitude of Vc is equal to square root of VCM square plus what? Vt square. Vt is R omega. So write it as plus Vt square or square root of Vm square plus R square omega square under root. Is it clear? When they are perpendicular to one another. When they are perpendicular to one another, two vectors. Right. Once again, here we did a small mistake here. You see, at A when they are in the same direction, this is I cap, this is also I cap. So we will not get this square root form of 2 times, square of 2 times. We get I if you take out VCM minus VT into I cap. So VCM minus VT whole square under root. So we will not get this one. This is small mistake happens. So VA is equal to, you can say under root of whole square is square root gets cancelled here. VCM minus VT. That's it. That is the magnitude. This can also be expressed as VCM VT is nothing but minus R omega. VT is nothing but R omega. This gives the magnitude when we still in opposite directions. In the previous case, it is not in pure rolling case, but in general case. But pure rolling case, those two are equal, so VA is equal to 0 in pure rolling. These points we try to remember. Okay. And a few more additional points are there. We have just 5 more minutes. We will try to discuss next one simple point. Whenever the body is in pure rolling, what will be the total energy? Total energy of the body. So write down next the point. So can I write this? When the body is in a rolling motion, what is the total energy of the body in rolling motion? Total energy, write down subheading. Total energy of the body. So that's T. As the body is moving forward, that is in translation motion and also rotating, and that is in rotational motion, total energy of the body is equal to the kinetic energy due to translation, that is translational kinetic energy plus kinetic energy due to rotation, rotational kinetic energy. It is equal to sum of translational kinetic energy plus rotational kinetic energy. Is it clear? So if a body having mass m, if let us say the mass of this body, the disc or the sphere, whatever it is, the disc let us say, the mass of this is mass of the disc. If you say it is a disc, then kinetic energy is half m into, it is moving under translation motion to velocity of VCM, so half VCM square. Alright? Whereas the rotational case, plus the rotational kinetic energy is, translational kinetic energy is half m v square. The rotational analog of mass is moment of inertia and rotational analog of velocity is angular velocity. So you can write it as half I omega square. half I omega square. Okay? In terms of V only, if you want to write this also, omega also as V is equal to R omega, omega equal to V by R, you can also write this as half M VCM square plus half I into Z, because V is equal to R omega, VCM is equal to R omega, omega equal to VCM by R, so square means VCM square by R square. Is it clear? So this way you can write the total energy in terms of linear velocity and angular velocity, or both in terms of linear velocity only, but here I is moment of inertia, that is another rotational parameter. And moment of inertia can be expressed in terms of r square or k square, radius of gyration. So if you replace this with in terms of radius of gyration, you write it as half m VCM square plus half into this mk square into VCM square by r square. So if you write half m VCM square out, then you can write half m VCM square into 1 plus z is k square by r square. K square by r square. This is another way of writing total energy of the body rolling. Pure rolling of m VCM square into 1 plus k square by r square, where k is radius of gyration and r is radius of the body. Got it? K will be different in different cases. If you consider the disk, for a disk rotating about center, what is moment of inertia for a disk? mr square. So K will be equal to r square. If it is rotating about, if you are considered rolling, it is considered to be like rotating about this axis tangent. There is a different. So accordingly K will change. So K is radius of gyration. So that you can take for different objects. Rolling motion of a disc or sphere or different objects, it will take different value. Okay? This is general expression for total energy of any rolling body. Okay? Right? Yes. So this is one of the very important points you have to remember, as almost the time up. So I am winding down here. So you guys go through the points, the basic points related to already which we have discussed earlier, and these points which we have discussed about rolling motion. There are some cases you may come across where the body is under rolling motion in inclined plane also. Inclined plane case. That takes a different expressions. So that is just you can go through once, but this is a simple basic relation.